Welcome to the lecture on quantum algorithms. After a short high-level introduction, we'll quickly look at some quantum complexity classes, and we'll see two of the most important algorithms that have been developed in quantum algorithms, which is Shor's algorithm and Grover's algorithm. And then we will see how to use especially Grover's algorithm in order to solve some NP-hard problems. And we'll see some speedups that we can get for our branching algorithms and for our randomized algorithms. So traditionally, a classical bit is either a 0 or a 1. And you can see here a strange figure where on the x-axis I have the probability that this bit is 0, and on the y-axis I have the probability that it is 1. So my bit is always in one of two states. So either it has a 100% chance of being 0 and 0% chance of being 1, or the other way around. So these are my two possible states of a bit. Now, if we think about a random bit, before we actually read it, it has some chance of being a 0 and some chance of being a 1. For example, if we generate a bit uniformly at random, it has 50% chance of being a 1 and also 50% chance of being a 0. So its value can be thought of as lying on this line. If we look at a quantum bit or a qubit, those take values somewhere on this unit circle. And typically this is represented as a vector going from the origin to a point on this circle. Now, these probabilities are not really probabilities anymore. They are amplitudes. And you can see that they can become negative. And the property is that, well, we have a circle here. So the property is that the square of the absolute values of these amplitudes sum up to 1. So our quantum bit is in a superposition of 0 and 1, and this is described by two complex amplitudes, alpha and beta. These are complex numbers, but for algorithmic and complexity purposes, we can think of them as real numbers. It doesn't make a big difference for us. So the status of our bit, of our qubit, is alpha times ket 0 plus beta times ket 1. And we have the property that the absolute squares of alpha plus the absolute square of beta is equal to 1. One peculiar thing is that as soon as we read a quantum bit, the superposition collapses. So for example, if we read the qubit in the standard basis, ket 0, ket 1, its value instantly becomes either ket 0 or ket 1, and it becomes ket 0 with probability the square of the absolute value of alpha, and it becomes ket 1 with probability the square of the absolute value of beta. Now, a set of n quantum bits can be described by 2 to the power n complex numbers. So for example, if we have 2 qubits, then we have some amplitude associated with the state 0, 0. So maybe we call this alpha 0, 0. We have some amplitude associated with the state 0, 1. We have some amplitude associated with the state 1, 0. And finally, some amplitude associated with the state 1, 1. And we also have the sum of the squares is equal to 1. So you can see that with 2 qubits, we have 4 possible we have 4 amplitudes. So and in general, with n quantum bits, we have 2 to the power n amplitudes that are associated with the state of the whole system. But now, these quantum bits can actually be entangled, And that makes it sometimes impossible to describe the system as the product of n individual qubits. So to describe your system on n qubits, it's not sufficient to just write down the amplitudes of each qubit because they actually depend on each other. But reading some of these qubits collapses their state, as we saw earlier, and the remainder of the system becomes instantly consistent with these new states. And no matter the distance between the qubits, and that's Einstein's spooky action at a distance. Now, how can we compute with our qubits? Well, we can initialize them. And then there's reversible unitary transformations, which basically means you multiply your state by some matrix that preserves this property. And more generally, this property for a system of n qubits. We can transfer our qubits, we can do input-output operations, and we can measure them. And so measuring them means reading their value. So we can read them in the maybe 0-1 basis, but this collapses their state. So if we want to preserve this complexity here, then we cannot read them too early. And typically algorithms would make a lot of operations with their qubits and then read in the end only. But we will leave further details about quantum circuits, which is the typical model of computation that's used for quantum algorithms. We leave that out of this lecture, and there's excellent expositions by real-world leading experts that you can find online. So let's have a little look at the main complexity class associated with quantum computation. So here we have our class P, polynomial time computable problems. For randomized algorithms, there's the bounded error probabilistic polynomial time class. So that's the class of decision problems that can be solved by a probabilistic or randomized Turing machine in polynomial time with error probability at most 1/3. The exact number here doesn't matter. The important thing is that it's less than 1/2. So we allow two-sided error. So as soon as we bound the error away from 1/2, we can just run the algorithm multiple times to make this error probability arbitrarily small. And then the analog for quantum algorithms is BQP. So that's bounded error quantum polynomial time. So that's the class of decision problems that can be solved by a quantum computer in polynomial time with error probability at most 1/3. And we typically speak of a bounded error quantum algorithm with a certain running time. So if it's polynomial time running time, then we have shown that the problem is in BQP, but we'll also talk about bounded error quantum algorithms with exponential running times. So can our polynomial time quantum algorithms solve problems that are NP-complete? Well, it's not believed to be the case. So it's believed that NP-complete problems do not intersect with BQP. So no NP-complete problem can be solved in polynomial time on a quantum computer. We also expect that, well, randomization doesn't add much power beyond P, so we actually expect that BPP is equal to P. But we don't expect that BQP is equal to P as well, and actually there are problems like Fourier sampling and Fourier checking, that are candidates for belonging to BQP, but not even being in NP, let alone P. So there could be problems that are in BQP, but not in NP. So the first algorithmic result that I want to mention is Shor's algorithm. And it's about prime numbers. What's a prime number? Of course, a prime number is a natural number greater than 1 that is not the product of two smaller numbers. So, for example, 4 is, of course, not prime because 4 is 2 times 2. So it's the product of two smaller numbers. Whereas 5 is prime because, well, if you want to factor it, maybe you can say it's 1 times 5, but yeah, so 5 is not a smaller number than 5 itself. Prime numbers have been well studied, of course. So computationally, so one problem might be to say if we are given some number, some natural number, is it a prime or not? So the problem is called primality test or primes. The input is an integer n, capital N, and the question is this integer a prime number? The input size is the number of bits we need to represent this integer. So the input size is small n, and that's the log of capital N. And then, so there's Agrawal, Kayal, and Saxena, who showed in 2002, and the paper was published in 2004, that primes is polynomial time solvable. So there is a polynomial time algorithm that does this primality test. And this is the first deterministic polynomial time algorithm for testing whether an integer is a prime. And the running time was O tilde of n to the power 12.5. The O tilde notation allows us to ignore factors that are polylogarithmic in the input size. And this running time has been subsequently improved to O tilde of n to the power 6. So I was studying back then, and it was really surprising that primes was actually polynomial time solvable, but by now it's already a quite old result. Now, integer factorization seems related, but actually it's a much harder problem. So the input is also an integer n, capital N, and the output is the prime factors of capital N. And this problem, it has a sub-exponential time algorithm, so it can be solved in time 2 to the order square root of n. And, well, if some reasonable assumptions are true, then the algorithm by Buhler, Lenster, and Pomerance actually runs in time 2 to the order the cubic root of n. Of course, we cannot really talk about integer factorization as being in P because, or in BQP because, well, these deal with decision problems. This is not a decision problem. So to make it a decision problem, we can look at the small integer factor problem. So here the input are two integers n and k, and the question is whether n has a factor that is smaller than k. And our current expectations are that small integer factor is not NP-hard. And that is because it belongs to both the class NP and the class co-NP. So it has small certificates for yes instances, and it has small certificates for no instances. So what's a certificate for a yes instance? A certificate for a yes instance would just be a factor that's smaller than k. And a small certificate for being a no instance would be a factorization of n into primes that are all larger than k, or that are all at least k. Okay, since we have small certificates for both yes instances and no instances, we know that the problem belongs to NP intersect co-NP. So if it were NP hard, then actually we would have that NP is the same as co-NP. We also believe that small integer factor is not in P, and this is just from experience of people who have been working on this problem for a long time, and think that really it's much harder than primes. Now, what if we have a quantum computer? Well, Peter Shaw showed in '94 that there is a bounded error quantum algorithm for integer factorization with running time order n cubed. And using a recent faster integer multiplication algorithm, the running time can even be improved to n squared times log n. And that's why small integer factor belongs to the class BQP. The algorithm in the quantum world is Grover's algorithm. So it solves the unstructured search problem. So what's unstructured search? Well, the input is given in a strange way. So we have access to a Boolean function. x1 to xn are Boolean values, and this returns either 0 or 1. This word that we have access only to this Boolean function, and we are not given a description of this function, means that, well, we have to treat this function as a black box. So we are not allowed to look at how it works. So it could be the case that this function is given to us via a circuit, via a Boolean circuit. And this would be often the case because for quantum algorithms are often described as circuits with quantum gates. And so it's very natural that f is given to us as some Boolean circuit. So we have access to this Boolean circuit, but actually we're not allowed to look at the circuit itself. Now, the output is an assignment from these Boolean variables to 0 and 1, such that the function evaluates to 1, if 1 exists. So it's like kind of a circuit satisfiability problem, but we are not allowed to look at how this function is computed. Since we know nothing about the function, we just know that it always evaluates to either 0 or 1. Any classical algorithm would need 2 to the power n time to find a satisfying assignment. But in the quantum world, there is actually a bounded error quantum algorithm for unstructured search that uses only order 2 to the power n half evaluations of f. And if f can be evaluated in polynomial time, for example, if f represents a set formula in conjunctive normal form, then we can easily, for a given assignment, evaluate it in polynomial time. Right? And for our NP-complete problems, if we're given a candidate certificate, we can always check whether it's a valid certificate in polynomial time. So that's why this is quite surprising, because now we can cut down the running time of set to order 2 to the power n half if we have a quantum computer. So as a corollary, we have that satisfiability can be solved in this time, and so people say that we get a quadratic speedup for satisfiability. But that seems to be kind of the best that we can hope for if our current thinking about quantum computers is right. There's also the quantum strong exponential time hypothesis, which basically says that we cannot hope for any faster algorithms than this. So there's no bounded error quantum algorithm that solves satisfiability with n variables in time 2 to the power 1 minus delta times n divided by 2 for any delta greater than 0. So basically, this is the best constant, so this square root of 2 to the power n that we can hope for. So now we are going to see how we can use Grover's algorithm and similar methods to speed up some of our other algorithms. So we have seen branching algorithms quite a lot. So what's a branching algorithm? Well, we first select some local configuration, then look at which values can this local configuration take, and then we solve subproblems where we have fixed this local configuration to take some values. In the end, we'll combine the solutions to the subproblems into a solution for our original problem. And now we look at a specific class of branching algorithms that require that this combination step at the end is just a simple OR. So it's just a disjunction of the solutions that we find. So basically, our algorithm will return yes if for at least one of the subproblems we returned yes. So this is really a search problem, because basically we are looking for a solution, and well, if in at least one branch we found a solution, then we are happy and we get a solution overall. So this, since we have a disjunction here, we can encode having a solution as just returning yes. So this is really a search algorithm where we are looking for a solution. There's branching algorithms that work in different ways. For example, you could think of some branching algorithms that compute, let's say, the number of dominating sets in a graph, and maybe one branch computes the number of sets that may or may not dominate the whole graph, and another branch computes the number of sets that do not dominate everything. And so in the end, we return the difference between these two. But so many branching algorithms search for a solution in this way. Okay, so what's known for branching search algorithms? Well, there's Führer's algorithm that says if we have such a branching search algorithm that spends only polynomial time at each recursive call or at each node of the search tree, and we also have a measure mu such that for each instance I, the search tree of A executed on instance I has at most 2 to the power mu of I nodes. So this is the number of nodes of our search tree. Then there's a bounded error quantum version of A with running time 2 to the power mu of I divided by 2. So we get a quadratic speedup instantly for branching search algorithms. So classically, we would need 2 to the power mu of I time, But now in the quantum world, we need 2 to the power mu of I halved time. So Führer's algorithm actually needs to know mu. And so mu is something that we typically obtain from our running time analysis. Maybe we used measure and conquer to analyze the running time of our branching algorithm. And so mu is the measure that we used. So the way that Führer's algorithm needs to know this is because, well, it wants to direct the algorithm towards the part of the search tree. So if there's, for example, a search tree where we have 2 branches for our top node, and let's say one part of the search tree is much bigger than the other one, then we want to make it more likely to use, well, the left path, the left branch here. Because somehow we want to equalize the probabilities of arriving at each leaf node, because at leaves is where we find potential solutions. But actually, this knowledge of U can be avoided. So there's variants of this algorithm that don't need to know mu, but they can instead use tree size estimation. So they would estimate the size of this tree on the fly by doing a little bit more computation in polynomial time. Okay, so now using Führer's algorithm, because many of our branching algorithms are actually branching search algorithms, we get an instant quadratic speedup if we have a quantum computer. For example, we saw an O star of 4 to the power k time algorithm for max-leaf spanning tree, and so this now becomes a bounded error 2 to the power k time algorithm for max-leaf spanning tree on the quantum computer. We can also look at our randomized algorithms and see whether they can get a speedup similar to our branching algorithms. So again, we assume that we have access to a Boolean function f. And now, instead of having a branching algorithm, we have a randomized guessing algorithm. And so let's assume that it has success probability at least p of guessing correct values for x1 to xn, such that our function evaluates to 1. So for our classical randomized algorithms, we need to run our algorithm the inverse of the success probability many times, so that we get constant success probability overall. So we need order 1 divided by p executions of this algorithm, and then we get constant success probability. But so Brassard and others have shown that in the quantum world, there is a bounded error quantum algorithm that finds values for x1 to xn, such that the function evaluates to 1, using only the square root of this many executions of A. So we only need the square root of 1 divided by p many executions in order to get constant success probability. And so similarly as before, this algorithm also does not need to know the success probability of the original algorithm, but instead it can be estimated on the fly. There's a tight relationship between these branching search algorithms and this kind of randomized algorithms. So let's say that we have some branching algorithm. So with some search tree, and we want to turn it into a randomized guess and check algorithm. So then what we can do is, well, we can start here and we can take a random path from the root of the search tree to a leaf. But again, so we can see that there's more leaves below the left branch than below the right branch. And our goal is to reach each, so ideally we would reach each leaf with equal probability. So we have the same probability of reaching each leaf. We don't know where our solution is, if one exists. So we just try to equalize this probability. Or you could think of we maximize the minimum probability of reaching each leaf, which amounts to equalizing their probability. Okay, so we want to make it more likely that the algorithm chooses the left path than the right path, because that's where we have more leaves than here. In general, of course, we don't know how our search tree looks when we start, but if we think of Führer's algorithm, for example, we can use a measure to basically measure how complex our instance still is. And so the measure, 2 to the power measure is an upper bound for the number of leaves. And we'll use this upper bound to inform the choice that we make. So if 2 to the power mu of this instance is much larger than 2 to the power mu of this instance, then we make it much more likely to go to the left. So, okay, so we can think of a randomized algorithm as traversing our search tree and arriving at a leaf. And now, once we are at a leaf, of course, we can check in polynomial time whether we have found a solution. So it's not very surprising that these branching search algorithms and these guess and check randomized algorithms give us the same quadratic speedup in the quantum world. Okay, so now many randomized algorithms also get a quadratic speedup on quantum computers. So for example, if we take our O star of 4 to the power k time randomized algorithm for feedback vertex set, now we obtain a bounded error, O star of 2 to the power k time algorithm for feedback vertex set. That's just because so 2 to the power 1/2 is 4 to the power 1/2 is of course 2. What else has been done regarding quantum algorithms? Quantum walks. They are a generalization on quantum computers of random walks. So sometimes our fastest classical algorithm doesn't use branching search and doesn't use randomized algorithms. So what people sometimes do is, they look at the fastest known algorithm and try to see, is there a branching search algorithm or is there a randomized algorithm that has the same running time? And if so, we get the speedup, this quadratic speedup immediately. And sometimes that doesn't seem possible, but maybe we can replace parts of that algorithm by one of these algorithmic methods where we do get a quadratic speedup. And then recently, people have started to introduce quantum parameterized complexity. So that's a team around several researchers from UTS who is doing this. Okay, that's it for the quantum lecture, and these are the references that I used.